So here's what we've got. Turns out we're going to go ahead and define line segments, specifically the sum of line segments. Now we've done this before, and this definition that we have is very, very similar to what we had before. So here's what we've got. First of all, we're going to look at the congruence classes of line segments. Now I am not assuming that you necessarily know what a congruence class is. I'm going to give you the layman's definition of what a congruence class is. We're going to assign every single line segment in our geometry a length, and we're going to assume we have a distance function in the Hilbert plane so that we can do that. And then all of the line segments that have the same length, we're going to throw them in the same pot, and we're just going to play with them or deal with them by way of their length. Okay? That's roughly speaking what's going to go on here. So we've got two different line segments, length of the first line segment represented by an A, length of the second line segment represented by a B. And how we're going to do this is we're going to grab two line segments. And specifically, we'll go ahead and label this as points A, B, and C. So here's point A, here's point B, here's point C. And we're told that line segment AB has a length of A. That's this bit right here. And this then says we have line segment BC. We'll go ahead and say that it has a length of B. Then if you take the sum of these two line segments, and we know that our sum of line segments based on previous definitions, so AB plus BC, we know that would be the same as A to C because they're all on the same line. If they were not, if points A, B, and C were not currently all on the same line, you would move one of the line segments so that it was extending the other line segment. In other words, you'd move it so it's actually in this orientation. So the sum of the two smaller line segments is the larger line segment. Now, what does this last bit tell you? It says, hey, this guy AC, that's totally going to correspond or have the same length as A plus B. That's all it's saying. In other words, you can totally manipulate your line segments based off of their length, is the conclusion or the takeaway from this definition. Now, once you have your definition of your line segments relating to a congruence class, then we come down and look at the first of two propositions that we have in section 9. It says, suppose you're in some Hilbert plane. Then when you're adding line segments, you have the following four properties. The first one says you take any two line segments or the length of any two line segments, and that sum is always well-defined. Well-defined is just a math term for saying you get exactly one answer. You don't have any sort of question mark here on what is the answer in this situation. The second thing we know, or we're told we have, is that addition is commutative. In other words, it doesn't matter the order in which you add the two lengths of line segments together. We're also told addition is associative. So if you have more than two line segments, it doesn't matter which pair of line segments you add together first. Remember here, or notice here, that the sum of line segments, or addition in general, is a binary operation, meaning it's defined on exactly two objects. So if you have more than two objects, this associativity property starts coming into play. But as we know, we almost always add more than two objects, or we frequently add more than two objects is probably the smarter thing to say. Fourth property says, hey, you've got the lengths of any two line segments. Then you're going to have exactly one of the following three cases, where the last two look a little bit funky, but I'll explain what they are. The first case is your two line segments might be congruent, so their lengths would be the same. Second case here, where it says A plus C equals B, that's a fancy way of saying that length A is less than length B. So this is exactly the same as saying that the line segment whose length is A is shorter than the line segment whose length is B. And any guesses what this last part C would represent? Yep. So in this case, this one would say that A then is the line segment that is longer. So both of those two guys are just fancy ways of saying inequalities. Now, how would I know that they are fancy ways of saying inequalities? Think back to line segments. If A and B, or A, B, and C, or A, B, C, and D all represent lengths of line segments, what do you know about those type of numbers? Any guesses what criteria you would know about your lengths of your line segments? In other words, could they ever be negative? Oh, they can't be negative. So one of the things we know is that these A, B, C, and D letters are representing the lengths of line segments. This means they're all going to be positive or larger than 0. Okay? Now, depending on the type of field that you're working in, you may have to define what being positive means, but in any type of number system you have, I shouldn't say that, in many types of number systems you have, you'll be able to find some numbers that represent positive numbers. For us, we're going to be dealing with rationals, so fractions up to real numbers, and we know that real numbers to fractions designated, we know who's positive and negative, don't have the negative symbol out front, basically. Okay. So that's proposition 19.1. Now, this title up here for section 19 includes both addition and multiplication. So while addition was pretty much the same as before, except with the new terms of the equivalence classes, multiplication is actually something we haven't done before. So this one's properly new. Let us scroll down right until we get to the last proposition. So product of line segments. So this one here, again, says we're going to start off that we have congruence classes of line segments. In other words, you've got a line segment whose length is A, you've got another line segment whose length is B. And here's how this one is put together. Feels a little weird. Okay. First thing is we're going to have a right triangle ABC. So let me go ahead and draw a right triangle in here. Pretend those lines aren't wiggly. Okay. And we're told that angle B is the right angle. And I'll go ahead and have AC be then the other two vertices. Oh, that's not a C. A to C. Not allowed to have two different vertices of a triangle of the same letter. All right. So we're also told that the length or the distance from A to B is supposed to be 1. And we're told that the distance from B to C, or the length of line segment BC, is supposed to be that guy A. Okay. That's the original setup. Now, we're also told, because we're super lazy, that we want to label the angle A with a little alpha, just to make our lives easier in the future. Then we have a second sentence down here on this, starting at the end of the second line and really mainly on the third line here. And it says we want a second right triangle. I'm going to try to square this one up a little bit better. Nope, still wobbly. All right, so this one here is triangle DEF. E is going to be the right angle. Let's put D on the base, which means F has to be up top. And for this guy, we're told that the distance between D and E is length B. We're told that angle E is the right angle, and the angle at D is exactly the same as the angle at A in the other triangle. So yes, I realize my two triangles are not to scale. Okay. Now, we then define the product AB in the following way. That product AB is going to be the distance from E to F, or the length of line segment EF. Now, at this point, we haven't talked about similar triangles in any sort of official capacity yet. We did it once when we were talking a little bit about section 13 stuff, and that was when we were in the real Cartesian plane and we sort of had a hiatus back to like high school geometry. But in terms of properly of things that we've allowed to use yet, similar triangles has been something we've been avoiding because we just haven't established the stuff yet. But if we had similar triangles, so there's the big keyword, if, notice if you look at those two triangles, I'm going to claim that they would actually look like similar triangles. Okay? Notice the little one down here is, I don't know what the hypotenuse is, but the two legs have length 1 and A. It's got a right angle, it's got an angle, whatever alpha is. We could totally figure out what the angle at C up here is. We're not told, but we could figure it out if we wanted to. Okay? Now in the bigger triangle, we also have a right angle. We also have an angle alpha. Again, we don't know what this angle is here at F, but if we needed to, we could totally figure it out. Notice, though, if you look at the two legs of the right triangle, they look exactly the same as the length of the little triangle, except no, of course, I'm lying. What happens? They're scaled up versions. So here, we multiplied the 1 by B, and on the upright or vertical leg here, we multiplied the A by B. In other words, it looks like two similar triangles, where the larger one here was all of the sides of the smaller one, but multiplied by that factor of B. Now, while you may believe that logic, technically speaking, we probably shouldn't have said it like that, because this just illustrates what's going on by way of similar triangles. But it turns out logically we went the wrong way with that analysis. Turns out this guy here of defining a product of line segments in that particular manner is why similar triangles actually works. It's not a result of similar triangles like what I just explained, but instead it's the sort of foundation behind some of the stuff that we do with similar triangles. Okay? It's this, in terms of implication, I reverse the arrow type thing. Okay? Now the nice thing is when you build a picture, if you already are thinking similar triangles, it's of course similar triangles. So it's a nice little way of describing and having you believe the picture. Okay? But that would be how you would deal with product of line segments. And once you've defined your product of line segments, turns out you get some results. And let me make sure it's actually up here too. It turns out in order to have this work right in that definition of dealing with your product of line segments or multiplying line segments, you do actually need Playfair's axiom to be involved. You can define some of the other things, but in terms of getting all of your properties, you need to go ahead and have Playfair's axiom involved. So you get 6 properties here, or 6 results. The first one is the product of any 2 line segments. And when we say line segments here, we do mean the length of one's line segment times the length of the other line segment is well defined, or there's no ambiguity of what the answer is. There's exactly one answer. Second property we get is you take your number 1, you multiply it by the length of any line segment, you still get that same old length. Third property says if you multiply the length of any 2 line segments together, it doesn't matter which one you multiply first, which one you multiply second, you're still going to get the same property. So commutative. Multiplication is also associative. So if you've got 3 line segments you need to multiply together, it doesn't matter which 2 you multiply together first, and then do it with the third one. Fifth property says if you pick any length of any line segment that you have in your geometry, you can find the length of some other line segment where this equation works. In other words, A times B equals 1. What this actually tells you here is that B equals A inverse. And then lastly down here you have the distributive law. So you have A times B plus C. You can actually distribute that A on B and on C and expand out right here. Now, some of that stuff should look familiar, hopefully. The conclusion here that we get is the set of all your line segments. And when I say line segments, I really mean the congruence classes, which if you prefer, are going to be the lengths of the line segments. With respect to addition and multiplication like we just defined. So as defined above, turns out to be a field. The nice thing about a field is it means all of your objects in your field are going to act just like the set of real numbers. The addition will act nicely, the multiplication will act nicely, and they'll interplay with each other exactly like you would expect everything to happen. The thing about fields is those are the type of numbers that even if they look weird and crazy, they will act exactly like you would expect numbers to act. Okay? So what this tells you is all that stuff that you've wanted to do since before our class started where you just say, hey, I can label my length of my line segment with maybe a lowercase letter and then do some algebra on it. Now we're going to be able to do all of that. Okay? Before, technically speaking, every time we did some algebra on the stuff, unless we were being very, very precise, we were totally sort of just doing cheating or scratch work. Now we have the results where we can actually do all of that stuff properly. And that's it for section 19. It basically just says do what you always wanted to do. Now, the next section that we want to go over in brief is dealing with similar triangles. And there's only a couple things that we want to talk about with similar triangles. There's two main facts that we need to worry about, and I'll go ahead and show you some of the other main ones, but not focus on them. Okay. First thing is, can't deal with similar triangles until you know the basic notation. There's three main things that you'll see in our textbook. The first one is dealing with the length of the line segment. That's exactly what we just talked about. Maybe we say A is the length of line segment AB, maybe B is the length of line segment CD. So here's the properly new things, ratio and proportion. Ratio of two line segments, or ratio of two sides of a triangle, which is where it'll come from, is where you literally are forming some sort of fraction with these two lengths. And since we just found that the lengths of line segments form a field, this means that this fraction AB, you could actually simplify it and it'll be some number in that field of line segment arithmetic. Now, proportional is the last buzzword that we're going to need to worry about, because this occurs in tons and tons of the propositions associated with similar triangles. So if you ever need to use one of those propositions, you'll probably see this word. Okay. So suppose you have 4 lengths of line segments, so potentially all different. These guys are called proportional if you're able to form 2 different fractions from the 4 lengths of your line segments, and those 2 fractions or those 2 ratios are equal to each other. And that's it for the terminology. Now, next thing is definition of similar triangles. I am assuming that you guys are familiar with similar triangles, but just to make sure we have our formal definition, 2 triangles are considered similar if all of their corresponding angles are congruent to each other. So far, that's the same as congruent triangles. Here's the part that's different from congruent triangles. And the ratio of all their corresponding sides is all the same for all 3 of the sides. So let me draw in a little picture because I didn't leave myself enough space for this. Suppose you have a triangle that looks like this. Maybe this is A, B, C. And I'm going to do a scaled up version of this guy, pretend that looks the same. So here's our B prime, A prime, and C prime. So this tells us the angle at A and A prime have to be congruent. The angle at B and B prime have to be congruent, and the angle at C and C prime have to be congruent. Now, your sides don't have to be congruent, although technically every pair of congruent triangles is also a pair of similar triangles. Realistically, you just go to congruent triangles at that point. Okay. Now, in terms of the corresponding sides, the side tagged with a lowercase a would actually be side BC. Sorry, that kind of smudged a little bit. Why do I know it's the side BC? Because that's the side that's opposite point A. It's also the side that's name doesn't include an A. So the side designated with a lowercase a prime would be the same B prime C prime side. The side across from point B would be tagged with a length of B. Same deal in the primed version. And the side across from vertex C would be tagged with a length of lowercase c, and same deal in the larger triangle. So notice here your corresponding sides are the sides between the corresponding angles as well. So that's another way to think about it. And in terms of symbols, when we say that 2 triangles are similar to each other, the symbol between there looks almost identical to congruence. The only difference is there's no equals under that little tilde. Just like if you had a less than or equal sign, you'd take off the equals if you just wanted it less than. Same sort of idea. Now, the first big property that we care about is that proposition 20.1, or it actually has a name, angle, angle, angle. Just like we had triangle congruence theorems where we had, side, 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 angle, side, angle, side, etc. This one here, though, doesn't give you a pair of congruent triangles. It gives you just a pair of similar triangles. So if all 3 of your corresponding angles are congruent, then your two triangles are similar. Notice what this gives you, just like with the triangle congruence theorems where you only have to check half the information from the definition. Here, you only have to check what's going on with the angles. Automatically, this proposition tells you you'll get the ratios to be the same. Super, super, super important, used all the time with similar triangles. And the only comment that I've got with this guy is, and this happens quite frequently in this class, people like to use something called angle, angle. That's not actually a thing. It is something that you see back in high school, but it's totally a not real thing. It only works under a bunch of different stipulations, and it's like a, what's the way to say it? It's like a shortcut thing where you've combined several different propositions together. Okay, so not really a thing that you can use for our class. Now let's look at some of the other things. Theorem 20.5 talks about, hey, if you've got a Hilbert plane with Playfair's axiom, you'll get most of your similar triangle results. In Euclid, book 6, which we have been avoiding like the plague, that's where all the similar triangle results are. So if you need similar triangle results in your textbook, it's section 20. In Euclid's Elements, it's book 6. You can also, with similar triangle stuff, you can actually prove the Pythagorean theorem. You can do it with respect to line segment arithmetic. This would be the algebraic proof of Pythagorean theorem, where you don't have to construct tons of squares and triangles like we did at the beginning of class. Here you just use some algebra. And normally we talk about this, but we're going to skip similar triangles, so we're going to skip that guide tonight. Although your author does walk through it fairly nicely, so if you're interested in this guide, it's a pretty famous way of explaining why Pythagorean theorem is true. And your book actually talks about it 2 more times too. There's a lot of different ways that Pythagorean theorem is proved. Now, one of these guys that I did want to talk about is proposition 20.8. And it's not that proposition 20.8 is anything awesome and special. It's that I wanted to go over at least one example where we had to play around with the line segment arithmetic. Okay. So this guy is also somebody that we've seen back in Euclid. This is book 3, proposition 35 in Euclid. So what this says is, suppose you have some Hilbert plane, and since we are dealing with line segment multiplication here, we probably actually need Playfair's axiom too. So let me go ahead and put to the side here Playfair's axiom. So what this says is you've got some circle. You've got 2 chords, and those 2 chords intersect each other. I should have put in this point. Totally didn't happen earlier. Let's call it E, because that's the next letter in the alphabet. Okay? So they cut each other, or they intersect each other, or they divide each other into 2 pieces. So into segments of length A, B, C, and D. Now it matters where the A, B, C, and D are labeled, so let me go ahead and show you the trick. The trick is the first 2 guys, A and B, have to be on the same chord, and the last 2, C, D, have to be on the same chord. Doesn't matter which chord you pick. So for A and B, I'll go ahead and pick on chord A to D. So here's A, here's B. The order doesn't matter, you could have flip-flopped it. And then the last 2 guys, lengths C and D, we'll go ahead and call the lengths from B to E, C, and the distance E to C, D. So those are the 4 lengths now applied to the picture. You can see where they're at. And according to this proposition, if you do line segment multiplication, the product of the 2 pieces on the same chord is the same regardless of which chord you pick. So A times B is supposed to equal C times D. Such a weird property. Not going to lie, the first time I saw this, I did not believe it. But it turns out it actually works. So let's look through why this works. Let me go ahead and prove this proposition for us. The first thing is, let's go ahead and write down what we're given. So here we're given the circle, we're given the 2 chords. Technically we weren't given point E, so let's go ahead and say that's our intersection point. So 1. Consider a circle, and we weren't told the name of the circle, and I didn't write a name of a circle, so I have no name to write down right now, although we could name it. So with chords, and our chords were AD and BC. And we'll go ahead and say, let's let point E be their intersection. Now, it turns out the trick with this proof, just like a common trick that we did back in classical geometry, is when in doubt, try forming a triangle. Now, we also had the thing back in classical geometry of when in doubt, try drawing a circle. That's not a thing right now. So if we try drawing a triangle, it turns out there's lots of options to draw a triangle. In other words, connect some pair of points. So I'm going to go ahead and connect points A and B together to form the line segment AB. And it turns out we're actually going to want two triangles to be useful here. So let's do the one that's opposite. Turns out if you try to form the triangle that is adjacent or sharing a side with triangle ABE, it doesn't really help. So there now are two newly formed triangles. So let's write down what we did before we forgot it. So form line segment AB and line segment CD. Since we're in a Hilbert plane, that would be our first incidence axiom. Now, what did we do previously when we formed triangles? Well, we used to try to do things like side angle side or side side side. We would try to show that the two triangles were congruent to each other, and then we'd say, hey, well, once we know they're congruent, we get some results from the triangles being congruent. Those two triangles are not necessarily congruent to each other. In fact, if you look closely at those two triangles, assuming the blue line there were straight, what you would see is while they're close to being congruent, they're actually not the same size. They're not actually congruent. So instead of searching for congruent triangles, instead, we're going to look for similar triangles. And remember, the only thing you need in order for the triangles to be similar is you need all three of their angles to be correspondingly congruent. So corresponding angles are congruent is the other way of saying that. So what do you think? Of those two triangles, does it look like any of their angles are congruent to each other? You guys have a guess for any pair of angles that might be congruent? Yep. The easiest ones to spot are the ones at point E. So angle AEB, so that's the one up here in the top triangle, is going to be congruent to the one down in the bottom triangle. So that would be, what is that, CED. And they're vertical angles. Now, I have forgotten which proposition vertical angles is back in section 9 when we were building up to a Hilbert plane. But I do remember that this guy is Euclid's Book 1, Proposition 15, and that's just because I used it too many times out of classical geometry. So this is one of those things where you're like, all right, I know this came from Euclid, so that means it's not necessarily something that we can use in a Hilbert plane. So if you go back to our reference of all the things that we can do or have from Euclid in various Hilbert planes with various propositions attached, we notice that our proposition 15 from book 1 is actually in that interval right here of 2 to 21 from book 1. Hilbert plane, we're all set. We can totally use vertical angles. That would be one of the ways of using this reference of you go for the property that you want, and then you double check that you can actually use it. Now, that's one pair of angles that are congruent, but we have 3 angles in each triangle, so we need to look at the other angles as well. So maybe we look at angle A up in the top triangle, and we'll also need to look at angle B. Anybody have a guess what angle A might be congruent to, or which angle in the lower triangle angle A is congruent to? See? Yep. So here we have angle A. I attempt to bold that. Angle A comes and subtends this arc of B to D. And there's a property that says if you are an angle on the edge right here or on the circle, and you subtend some arc, any other angle that subtends that same arc will be congruent to you. So notice here if we look at C, C goes to that point B and D when its rays intersect the circle, so it subtends that same arc, which means our angle A is going to be congruent to angle C. Let me write that out. Angles subtending the same arc are congruent. And that citation turns out to be Euclid's 3rd book, Proposition 21. And if we looked it up in the chart, that would also be one we could use in a Hilbert plane. Now, using that same logic, anybody have a guess what angle or who angle B might be congruent to? So this one here would then be, we're hoping it's congruent to the one angle that we haven't looked at yet. And it turns out it is. Why? Because B and D, if you follow their rays over, they both intersect the circle at A and C, so they would still subtend that same exact arc. So B congruent to angle D. Now, at this point, we've got three pairs of congruent three pairs of congruent angles. Anybody have a guess what the next step would be? Yep, apply angle, 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 and applying angle, 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 that proposition, means you're going to get your two triangles, so triangle ABE and triangle CDE. I'm matching the vertices is what I was doing, matching congruent vertices in the same order. That those two triangles are going to be similar to each other. I'm going to claim there's two more steps and then we'll be done with this proof. Anybody have a guess what the next step might be? In other words, what's useful about getting similar triangles? It actually turns out to be the same thing we do with congruent triangles. You build up to use your proposition, in this case AAA, and then you pull some result from the definition of similar triangles. Yeah, so it's worded differently than what both of you guys sent in, but it's the right idea. So what we're going to do is we're going to grab our corresponding sides, and the official term here is your corresponding sides have the same ratio, or proportional is what's normally used. So your sides are proportional. Now that's going to be useful. Now let me write down why we can use that. That's just a definition of similar triangles. Now, why is that useful for us? Because we already have that the length of, well, 2 out of the 3 sides for both the triangles are given by those lengths A, B, C, and D. So saying that the sides are proportional or that the corresponding ratios are the same is going to give us some equation that relates the lowercase a, b, c, and d all together. So here, if we look at the triangle here up top, ABE, maybe we pick on the side AE, which is given by in lowercase a length of A. Well, this side corresponds to what side in the triangle CDE? A would correspond to what side? Anybody have a guess? Yep, it corresponds to the side E to C or length D right there. And I already prepped up the one other named side we had up here. So if we look at side BE, it had a length of C. Anybody have a guess which side corresponds to this length C down in the lower triangle? That would be B. So that just pulled the corresponding sides together and threw them into an equation. Now, this is not the equation that we were given up here in the statement of the proposition. The proposition claimed AB equals C times D. But could we get that conclusion from our equation that with the fractions that we have right now? And if so, any guesses how we could transform the thing with fractions into AB times CD? Okay, I got a couple different answers. So the sort of first thing to think about is this. doesn't look like it has any fractions. This guy totally does. So there's lots of different ways to think about it. The way that most people think about it is something like cross multiply. In other words, what did you do with that? You multiplied both sides by both b and d. So if you do a cross multiplication or multiplying both sides by both b and d, you will totally end up with exactly the equation you want. Now, here's where we are about to get precise with our reasoning. In the past, this is where we'd sort of throw up our hands and say, oh, we just did some algebra. Well, now we're going to actually be able to cite it for real. So this here is, what did we use? We used multiplication from the field of line segment arithmetic. It turns out you're only allowed to do that cross-multiplying, or multiplying in general, on your lengths of your line segments if you started off by having your line segments in some sort of field like what we built back in section 19. So this here's the proper way of what we in the past have just said, algebra. Note, we still did the same sort of idea. You still did exactly what you wanted to all the way down here. It was just being a little bit precise of how you cited it. And that's it. So this example here was mainly to look at how to play around with the line segment arithmetic, guys. Notice, wasn't anything fancy. So there's two more propositions that I wanted to look at in this section. The first one is one just to show you how to read it, how to use it. Quite honestly, the second one's going to be the same way. We're not going to prove either one of these guys. But we're actually going to use Menelaus' theorem, the one right down here. That's the big one we were building to tonight in this section 20. But first, let me show you how to read proposition 20.9. This is the same as Euclid's Book 3, Proposition 36, and this is one that we've actually dealt with way back in the past when we were in classical geometry. So here's what this says. This says, hey, you're in some sort of Hilbert plane, and you probably need Playfair's axiom with this one as well. You've got some point that's outside of your circle. You've got AB, you're told, is a tangent line to your circle, so it's only going to meet your circle in one place. You're also told here that the line AD intersects your circle in two places, so that's given ahead of time. Then the conclusion is you're going to get this equation right here, which, not going to lie, may seem a little ridiculous. Here's where this actually corresponds to the information over here. And of course, you can probably read it, but sometimes putting it in the line segment arithmetic will help. I'm going to go ahead and label the length of AB with a lowercase a. So notice this is the same thing as saying a squared equals something. I'm going to indicate the line segment A to C with a B, the line segment C to D with a little c. Now, A to C is this length B right there. But A to D is A all the way to D, so it's the entirety of the line. So this is B plus C. And I rewrote it that way because when people try to use this particular proposition, and it's one that's actually pretty useful, it's really, really easy to multiply this B times the C and leave off that plus B right there. That's the most common mistake that people use when they try to apply this theorem. But I wanted to make sure to show it to you if you ever need it in the future. But that's it for that proposition. Now the last proposition that we want to look at is Menelaus' theorem, and this guy is one that we're going to use when we jump into area. So what I'm going to do is I'm actually going to build up to that formula for us, and I'm going to walk it out or talk it out in a way that it will hopefully make it easier to apply this formula in the future, because this formula right here is really the big takeaway with Menelaus' theorem. So what you start off with is you start off with a triangle. Doesn't matter what triangle it is. There's our triangle. So A, B, and C, which isn't the best intersection in the world. Oh well. Okay. Then we have some line, and this line, L, is supposed to cut or intersect all three of the sides of the triangle. You should all be in utter disbelief for that because we know we're in a Hilbert plane here, we know that lines can't intersect all three sides of a triangle. So here's what we actually mean. We mean that the line will intersect two sides of the triangle, and then while it can't intersect the actual third side, if you extend that third side, then you'll be able to get your intersection. So that last one is sort of cheating. Then you'll be able to have one intersection designated per side. So here, if we go in order, AB would have an intersection at D with the line. BC, we'll call this one E. And AC, we'll call that intersection F. So that now labels the picture exactly the same way that the theorem is set up. All right, so now I'll go ahead and build to the formula. So right now, let's ignore this formula, and we're going to build our own. So here's how to use Menelaus' theorem. You have to have a triangle. You have to have a line that intersects two of the sides of the triangle, and then you either see that the line intersects the extension of the third side, or you force it by extending your lines until you get the intersection. So once you have this picture somewhere in whatever it is that you're dealing with, then you say, I know something about Menelaus' theorem. I'm going to have three ratios, or if you prefer, three fractions. We're going to multiply them together, and they're all going to equal 1 at the end of the day. Now, here's how you build the fractions. You pick one of the sides of your triangle, and it doesn't matter which one. So you guys pick. What side of this triangle would you guys like me to start with? Sure, we can start with AB. And if we start with AB, we're going to get the exact same format that we have up top. So what you do with your line segment, again, doesn't matter which one that you pull. You put one endpoint on the top of the line segment, on the top of the fraction, the other endpoint of the line segment on the bottom of the fraction. Okay, so you just have to split them. You could have also done B on the top and A on the bottom. It doesn't matter. You just have to have one of the endpoints up top, one of the endpoints down the bottom. Now the thing that you put next to these 2 points is, well, a second point, or really a third point, and we're going to build two line segments. So the point that you put here is the intersection of AB and your line. The intersection of AB and your line is point D. So we'll put point D here. Pretend that was actually a D. And now you've got two new line segments, and notice these two new line segments. It's where we broke our side up into two pieces. Now, at this point, everything else is predetermined. That first pick of which line segment to use, so which side to use, and which endpoint to put on the top and the bottom, those are the only two things where you get to make a choice. Now everything's predetermined. You look at the endpoint you have on the bottom of your fraction. The endpoint we have right here is a B. So you have to put a B on the top of the next fraction. There is no other thing that you can put there. So then you look and say, all right, well, what side of my triangle has B as one of the endpoints, but isn't the side AB? So what side of this triangle has B as one of the endpoints that we haven't used already? So this would be BC. So since B is already on the top, that means we'll put C on the bottom. And this is where you go and find the intersection of the line L and the side BC, or its extension. So what was the intersection of side BC and L? Anybody remember what that point is? That would be E. And then that gives us two new line segments. Technically speaking, you'll put the length of the line segments in these different fractions, but it was definitely easier just to put the name of the line segments here. Easier to remember too. Now, last fraction. We have a C on the bottom. This was the endpoint on the bottom of the last fraction we just built. So that means we have to put a C on top. So what is a side that we haven't used yet that has C as one of its endpoints? Hint, on the last fraction, it should be the one remaining side we haven't played with yet. Unless we completely messed up and made an error earlier. Yep, so this would be the line segment AC, or if you prefer, CA, so this guy right here. Now we've got the C on top, which means we have to put the A on the bottom. And here's how you know if you did stuff right, or where you hope you did things right. whatever endpoint you end up with here at the very end, so in our case the A, it should always match the very first endpoint on the opposite side of the fraction. So we started up here at the top with an A, we ended with an A, yay, this looks like we've done everything right. Now, last thing is we have to complete our 2 line segments. So here, the intersection of our line L and the side AC is be given by that F right there. And that is how you use or how you apply Menelaus' theorem. We're going to use this guy in the future when we get to area. We're probably not going to get to the example that I've got prepped up with area and show you how to use Menelaus' theorem tonight. It'll probably be at the beginning on Monday. Okay? But that would be how you would use Menelaus' theorem. Then you'd plug in the lengths of each of these line segments, or at least all of them you know, and you'd be able to calculate any missing lengths, is how we'll then use this thing. But that's it in terms of all the stuff that we're going to need to know for similar triangles. Questions so far? Feeling okay on how we went through Menelaus' theorem? That's the big one from this section. All right, so I don't see any questions, and we'll go over it again when we use it with that example with area too. All right, so the next part is where we finally get into dealing with area, and the first thing that we're going to talk about with area is, well, figures. So for us, we're going to be defining area on figures. We're not going to be dealing with circles, and in fact, based on how many days left we have in the semester, we're probably going to have to skip out on the section with circles anyway. Okay. So what we've got here is we're going to start off with rectilineal figures. We've actually defined rectilineal figures in the past, and I've told you, roughly speaking, they're polygons. And that's true. They have straight sides, so all of their sides are built from line segments. But here are some of the examples. Maybe you have something that looks kind of like a parallelogram. Maybe you have something that looks sort of funky shaped, kind of like the plus symbol. Maybe you actually have something that looks like a rectangle, and it's not one piece. Maybe it has 2 pieces. It looks like a rectangle and a triangle. Turns out all 3 of those guys, things between the commas, are all rectilineal figures, assuming that all those lines had actually been drawn straight. So it turns out the official definition is any figure that can be expressed as a finite union of non-overlapping triangles. So finite means it will stop. You can actually chop the figure up into a bunch of triangles. Non-overlapping is you're allowed to share sides, but they can't actually be on top of each other. So, and then this here just says you put them all together. So here's how you do that. If you look at the parallelogram, if we want to cut it up into a bunch of pieces, this is, you don't need to know this name, but this is called triangulation. I think I mispronounced that just slightly. What do? We just cut the figure up into 2 triangles. Could we have done more? Sure. We could actually do something like this. Not going to lie, the extra lines you have are probably going to make your life more miserable than not, but it depends on the context. Okay? This one down here, I claimed was also a rectilineal figure. Notice in this case, you're going to have more triangles because of all of those little rectangular pieces outside. So maybe you have something like this. And you probably didn't have to have that many triangles. You could probably make it a little bit better than that, but I was lazy. I thought of it in terms of a bunch of rectangles and put in diagonal lines. And then the last one, it's 2 pieces. That piece is already a triangle. And the piece next to it is some quadrilateral, so we can put in a diagonal and get 2 triangles there too. Now, then we can talk about interior points. And we've talked about interior points before with respect to triangles. Here it turns out if you want to point in the interior of any old rectilineal figure, it needs to be in the interior of one of those little building triangles. Now here's the fun part. Maybe something like that that's properly inside of one of the little triangles, but maybe it's actually on a line. So this second case right here, where that point was attempting to be on the triangle line, technically that's not in one of the interior of the little of the triangle, I can't speak, of the figure's little triangles. Okay? But it turns out that if this ever happens, what you do is you remove this line and you can redraw it with different little triangles. So it turns out this definition works just fine. And if you happen to have a point that lies on one of these lines, you just get a different way of cutting the figure up into triangles, and you'll still be just fine. So that's the basics on figures. Now, the first proposition in section 22 deals with, wow, how to deal with combining figures. It turns out the claim here is that if you take any two rectilineal figures and you look at either their intersection, their union, or their complement, turns out that new thing is still a rectilineal figure. In other words, it could still be cut up into triangles, or if you prefer, it still looks like a polygon or a union of disjoint polygons. Okay? Now I'm going to take this guy right here as an example. And let's assume that we have two figures, T for triangle, T for parallelogram. Don't overthink it. Okay? If we wanted to look at the intersection of T and P, or the triangle and the parallelogram, any guesses what it would be? And then we'll do the same thing for union and complement too. Any guesses what the intersection of those two figures would be? Well, hopefully you are all thinking where the overlaps. So I'm going to shade it in and then we're going to get rid of it. Okay. Yep. So this would be that little triangle where should not have written two B's. Let's go ahead and put a C there. That's definitely an issue. All right, so it would be that little triangle right there. So this one here, if we drew it out, it would look like A, B, and then what was supposed to be a C. Now, any guesses what the union of those two figures might look like? Not quite as easy as the intersection. Well, it would what? It would look like the outline, the outermost outline. So you'd have this thing that kind of looks like a parallelogram, but then you'd stop. So over here, we'd stop at C. Up here, we'd stop at A. And then we'd just follow the outer lines of our triangle. It would go something like that. Don't pretend that's an awesome picture. It's not. Okay. This guy, you could totally break it up in terms of a bunch of smaller non-overlapping triangles. So here's how you might do it. Here's maybe the line that you grabbed from the original triangle that we had. But over here for the parallelogram, or at least the part of the parallelogram we care about, then we go in and have to cut it up into some more triangles. Now, we could have done the exact same triangulation with the parallelogram up here, and then the parallelogram would have 4 triangles, those 3, plus the 1 additional triangle up there. There's a lot of different options here. Now, last thing is the complement. If we want to go ahead and look at the complement of T, complement of T can be done in several ways. You can put a bar up top, put a C there, or in our case, because we're dealing with respect to another polygon, what you actually want to write is what looks like set subtraction P minus T is our complement of T. What is that? It's simply your parallelogram, your figure P, and you subtract out everything that was in the triangle T. But if you subtracted out any line segments that should have been edges, put them back in. So that dotted line that would disappear with the triangle T, put that line segment back in. And this then would be your complement. And that's it. That's how you manipulate these things. Correct. So in terms of normal sets, your union would be something like you would add all of the points from the 2 different sets, and then you'd subtract any of the overlapping guys in the intersection. Here, I guess you could think of that behind the scenes, but it's not really that. You don't have that sort of overlap like you would in sets that are different. It's still the same underlying structure. So if you think of this as you have two copies of this set of this triangle ABC right here, you're not going to include both of the two copies, but since we're already in a flat plane, how would you draw two copies at the same point? So it's sort of like you do this less in college, but more in high school when you have like Venn diagrams and you chop it up into just a little part of the Venn diagram. Here, let me draw a picture. Just a little part of the Venn diagram that's over here, and then just a little part of the Venn diagram that's over there, and then just a little part of the Venn diagram there. That's sort of what we're doing here with geometry. Same sort of idea. All right, and almost the last thing that we're going to deal with in this section 22 is going to be dealing with the definition of equidecomposable. Equidecomposable is simply saying two figures are considered equidecomposable. The equi here is referring to equals. Decomposable here means you're going to be able to cut them up into pieces. So this says you can cut up your first figure into a bunch of non-overlapping triangles. You can do the same with the second figure. And it turns out they have the same number of triangles, and the corresponding triangles from the two different figures are congruent. Here's what that really means. You take one of the figures, you chop it up into a bunch of triangles, you take those triangles, you rearrange them, move them around, copy them around, reassemble them, and then bam, you found your second figure. Now, here's why we care about this. If two figures are equidecomposable, you're able to chop one up, rearrange it, form the new figure, they're going to have the same area. So what happens is when you have really weird figures and you don't know how to find their area, what can you do? Chop them up into pieces, find the area of the individual things, reassemble them if you need to, and that's how you can find area. So that's one of the applications that we'll see in the future. But let's look real quickly at this example, and based on time, we're totally just going to outline it. We're not going to do anything formal with it. So the question is, suppose you've got these two figures. One figure that's two congruent squares. The things that I forgot to write down apparently is that these two squares are congruent to each other. And they're squares. Over here, we also have a square. And that's just going to give us that all of the sides are congruent and all of our angles here are right angles. And the other thing that we're going to have is the line AC, which isn't drawn in yet, but is the diagonal of that first teeny tiny square over in figure P, is congruent to the side RS. In other words, we've got that and that. And according to this question, it says, hey, these two figures are supposed to be equidecomposable. Well, they're definitely not congruent. So equidecomposable is not the same as congruent. Every congruent pair of figures are equidecomposable, but non-congruent figures, in this case, can also be equidecomposable. It's like the next best thing to being congruent. So let's see if we can figure out what's going on here. First thing is you cut up one of your figures, or really both of your figures, into triangles. So let's do just diagonals right here, so as few triangles as possible. That's typically helpful. And I'm going to claim that if these two squares are really squares, we are going to automatically get all of our right angles. And if the two squares are congruent, that means our sides over there are all congruent, all 8 of those sides. If we look at the big square, all of our sides are going to be congruent and all 4 angles will be right angles. Okay? So let's go ahead and label these guys as T1, T2, T3, T4. Now, I'm going to claim that all of those triangles in the first figure, so figure labeled as P, are actually congruent to each other. Okay? Let's actually write down the stuff that we know. So we know the two little squares are congruent. Probably didn't need to rewrite that. But let's actually rewrite the name of the second square to something a little bit more logical. And we know that AC is congruent to RS. I am going to go ahead and claim that we have cut our figure P into 4 triangles, visibly obvious. And I'm also going to go ahead and claim that all 4 of these triangles are in effect congruent to each other. And there's a couple of different ways you can show that, but the easiest way is simply to use side, angle, side, where the angle is one of your right angles and the 2 sides are the 2 of the sides if you're square. And by the markings up here, you can see which ones correspond to which ones. Now, second thing is, let's go ahead and break up that second figure into 4 triangles as well. If the 2 figures are equidecomposable, they have to have the same number of triangles that they're cut into. So we have to be able to get 4 triangles. So I'm going to do the most logical thing, which is just put in the 2 diagonals of the larger square. And my very squiggly lines are supposed to be the diagonals. So here we can label these T1 prime, T2 prime, T3 prime, T4 prime. And this is where I'm going to skip steps. I am going to claim that these 4 triangles are also going to be congruent to each other. It turns out if you have diagonals with a square, and I think we had a homework example at the beginning of the course that dealt with this, turns out you'll get 2 things. One of the things is the 2 diagonals will be bisected. The other thing is you'll get right angles at the 2 intersection points. The intersection point right here. These right angles, that only happens if you actually have a square. So I'm going to claim here that these primed versions are all congruent as well. And you can also do that by several things. You might do something like a right angle, side, side. Honestly, I'd probably do something like side, angle, side as well. So maybe we say side, angle, side again. Okay. Now, if both of these 2 figures are broken up into 4 pieces, and all 4 pieces on both parts are congruent to each other, there's only one thing left to do. And that one thing left to do is simply to show that one of the pieces from the first figure, figure P, is congruent to one of the pieces from the second figure. And it turns out that is also true. Say you take T1 right here, that hypotenuse is congruent to that hypotenuse. Got a right angle, you've got a right angle, and it turns out you would be able to show you've got the other things as well. It's probably easiest to deal with angles. Those angles are going to be 45 degrees, and it turns out these angles here would also be 45 degrees. So that would be the last step right here. And once you've established that all 4 of those corresponding triangles across the 2 figures are congruent to each other, that then tells you that those 2 figures are equidecomposable, and this is how. You cut the 2 little squares in half, spin them around, and put them into that formation. That's it for the equidecomposable. Not going to lie, we totally skipped steps, but those are the big bullet points in terms of what you would be doing. The last thing in section 22, and then we'll end for tonight. And so next time, we'll get into working with area a little bit more properly. So I'm going to go ahead and skip that thing on equal content. We've talked about that before. Not that exact property, but equal content before. The last thing that we've got here is something called Desolt's axiom. So the Desolt's axiom says the following. It says you've got 2 figures. You've got one figure, which we'll call figure P. And I'm on purpose going to make it something obnoxiously large. Okay, that wasn't that large. There's figure P. And then you have a second figure that we call Q. And Q is supposed to be completely inside of P. So maybe Q shares the same side as P for a little while. And now I got too lazy to keep doing that. I'm trying to highlight where Q is. So maybe Q looks like a quadrilateral. So here's Q. So that would be the orientation of these 2 guys. So Q is a figure contained in another figure where P is a bigger figure. And if the complement of Q, this guy is your complement of Q, so the shaded part right here is that complement of Q. If that has a non-empty interior, in other words, you have at least one point, like point A, that is in P but not in Q, then it turns out that P and Q, the 2 figures, do not have equal content. Now, what did we say previously that equal content was? We've said since the beginning of class, every time we saw this phrase, equal content, that it's going to turn out to be the exact same thing as area. So what this says is if you've got two figures and you have one that's properly inside of the other, they're not going to have the same area. This here, this is totally going to be the backbone behind how we build to our area function, and we'll build up our area function and then use it next time. Okay? But that is it for tonight. That got us through sections 19 through 22 in your